At 0600 on March 27, 1945, Squadron Engineering Officer Darrell W. Landau stood next to a smoldering Wrighter 3350 engine at Northfield, Guam, observing mechanics remove the scorched remains of cylinder number 14. 31 years old, 6 months with the 19th Bombardment Group, 18 burned-out cylinders replaced in the past week alone. The Japanese had destroyed 14 B-29s over Tokyo in the previous month. Engine fires had consumed 23. Landau had witnessed 5 Superfortresses incinerate on this runway since February. Magnesium crankcases igniting at 5,600 degrees Fahrenheit, main wing spars reduced to ash in seconds. Crews perishing before they cleared the tree line. The sequence was always the same: rear cylinders overheating on takeoff, valves failing, fire spreading faster than the extinguisher systems could react. By the time a pilot feathered the propeller, the wing was already compromised. Wright Aeronautical had issued 48,000 engineering modifications to remedy the UR-3350. New baffles, revised exhaust collectors, tighter cull clearances, different carburetor elbows, none addressed the underlying issue. Engines that had averaged 100 hours between overhauls at the war's outset now lasted 400. 400 hours remained catastrophic for a power plant expected to fly 3,000 miles to Tokyo and back. The tropical heat exacerbated everything. Guam's runway temperature reached 125 degrees by mid-morning. Pilots taxied as rapidly as possible to the run-up positions. Flight engineers monitored cylinder head temperatures climbing past the red line during every takeoff. There was no margin, no safety buffer. Every mission began with engines already on the edge of failure. Landau had studied the official reports from Wright Field. Their solution was fuel injection. Replace the entire carburetor system and retrofit every B-29 in the Pacific. The conversion would take months, cost millions, and require pulling bombers out of combat rotation during the most crucial phase of the war. But fuel injection corrected the fuel-air mixture problem. It did not explain why some cylinders overheated while others did not. It did not account for the pattern Landau had observed. Cylinder number 1, positioned directly behind the largest obstruction on the engine, almost never failed. The cylinders that burned out were consistently positioned elsewhere, counterclockwise from the front view. If you want to see how Landau's observation played out, please hit that like button. It helps us share more forgotten stories from World War II. Subscribe if you haven't already. Back to Landau. The mechanics were lifting the damaged cylinder onto a workstand when Landau looked up and noticed the massive propeller governor and the twin distributors mounted on the front of the engine, components the size of footballs obstructing the airflow. And he realized, the UR-3350 displaced 3,350 cubic inches in 18 cylinders arranged in 2 rows, producing 2,200 horsepower, all dependent on air passing through a cowling designed before anyone understood what maximum weight tropical takeoffs would demand from cooling systems. That air had to swirl, had to navigate around obstructions, and it swirled counterclockwise every time on every engine, bypassing the exact cylinders that kept failing. Landau studied cylinder number 1 with its thermocouple sensor, the cylinder Wright Aeronautical had designated as the worst-case indicator, the cylinder that should overheat first, the cylinder that almost never overheated because it sat in a dead zone directly behind the blockage where the swirling air never reached. He had the answer, the complete answer, and he had no certainty anyone would heed it. Landau had joined the 19th Bombardment Group in January when the unit arrived at Northfield from Peterson Field, Colorado. The assignment had seemed routine. Squadron engineering officers managed maintenance schedules, tracked parts inventory, supervised mechanics, ensured aircraft met combat readiness standards. Landau had anticipated paperwork and inspections. He had not anticipated witnessing B-29s incinerate. The first fire occurred on February 16. A superfortress named City of Angels, loaded with 10,000 pounds of incendiaries bound for Tokyo. The pilot advanced throttles to take off power. Cylinder head temperatures climbed past the red line as designed. Then cylinder 17 on the number 3 engine failed. The exhaust valve broke free. Burning gases ignited the magnesium crankcase. The pilot cut power and engaged the extinguisher, too late. The wing spar burned through before the aircraft reached rotation speed. City of Angels disintegrated at 130 knots. All 11 crew members perished. The crash investigation blamed worn valve guides, recommended more frequent cylinder inspections, and stricter temperature monitoring during ground operations, the same recommendations Wright Aeronautical had issued after every prior engine fire. Recommendations that changed nothing because they addressed symptoms rather than root causes. Landau began observing engine startups, not from the operations shack, not behind a desk reading reports. He stood on the hardstand, watched mechanics spin the propellers through compression checks, observed the ignition sequence, saw the cowl flaps adjust as engines warmed, and he noted the airflow, how exhaust gases swirled, how cooling air entered the NL and vanished into the intricate baffling system Wright engineers had designed. The baffles were intended to direct air evenly across all 18 cylinders, front and rear rows, top and bottom, creating uniform cooling even when the aircraft sat stationary in tropical heat. But the baffling assumed smooth airflow, assumed air entered the cowling unimpeded, without massive mechanical components creating turbulence and dead zones. Nobody had tested that assumption, not in tropical conditions, not at maximum gross weight, not with propeller governors and distributors sized for 2,200 horsepower mounted directly in the primary airflow path. Landau requested cylinder replacement logs that tracked every failure by position. Cylinder 1, 3 replacements since February. Cylinder 4, 11 replacements. Cylinder 7, 14 replacements. Cylinder 10, 9 replacements. Cylinder 13, 16 replacements. The pattern was undeniable. The cylinders positioned counterclockwise from the front view failed at 4 times the rate of cylinders in other positions. He presented the data to the group maintenance officer, showing the pattern suggested by airflow. The maintenance officer told him to focus on keeping aircraft mission ready. Engine reliability was Wright Aeronautical's problem. Squadron engineering officers repaired airplanes, they did not redesign engines. Landau returned to the flight line, back to observing engines run, and he saw it. During a morning engine start on March 21, cooling air swirled counterclockwise over the engine as the propeller turned, forming a vortex that directed air away from specific cylinders, leaving them dependent on secondary airflow that did not exist when the cowl flaps were set for takeoff. The worst cylinders were receiving no cooling at all. They overheated because air never reached them. Cylinder number 1, the designated worst-case indicator, cooled perfectly because it sat in still air behind the propeller governor where the vortex never formed. Wright Field had spent 2 years and 48,000 engineering changes trying to force more air into the cowling. Landau had just discovered they were forcing it into the wrong cylinders. He needed to prove it, needed to show someone authorized to fix it before another crew burned. The Writer 3350 duplex Cyclone was the most powerful radial engine ever mass-produced for combat aircraft, 18 cylinders, dual superchargers, twin-row configuration with 9 cylinders per row. Each cylinder displaced 186 cubic inches. The entire assembly produced enough power to lift 65 tons of bomber, fuel, crew, and ordnance off a coral runway and climb to 30,000 feet. The engine was also a metallurgical challenge: magnesium alloy crankcase to save weight, forged steel crankshaft running both cylinder rows from a single central bearing, exhaust collectors designed to capture gases from 9 cylinders simultaneously, and cooling baffles machined to tolerances measured in thousandths of an inch. Any one component failing could destroy the entire engine in seconds. Landau understood radial engine theory. Air-cooled designs depended on constant airflow across cylinder fins. The fins increased surface area, transferring heat from the combustion chambers to passing air, removing thermal energy faster than the engine generated it. Simple physics, effective when the aircraft was moving, catastrophic when stationary. Ground operations were always marginal. Taxiing at 5 knots provided almost no cooling. Pilots minimized ground time. Flight engineers monitored temperatures constantly, rushed through magneto checks, advanced throttles the instant they reached the run-up position. Even then, cylinder head temperatures climbed toward redline before the aircraft began rolling. But some cylinders reached redline faster than others, and those cylinders were always in the same positions, counterclockwise from front view, the exact cylinders Landau had identified from the failure logs. The propeller governor sat at the 12 o'clock position on the engine, a massive mechanical unit controlling blade pitch, converting engine RPM into thrust, essential for variable speed operation, and completely obstructing airflow to the cylinders directly behind it. The twin distributors sat at 11 and 1 o'clock, equally large, equally obstructive, creating dead zones where cooling air could not reach. Cylinder number 1 sat directly behind the governor. The thermolupple sensor recorded its temperature, transmitted data to the flight engineer's instrument panel. Wright Aeronautical had designated it the worst-case indicator because the engineers assumed it would run hottest. They were wrong. It ran coolest. The swirling vortex of cooling air missed it entirely, left it in still air that provided minimal cooling, but also minimal heating from adjacent exhaust flow. The cylinders that actually overheated were positioned where the counterclockwise vortex actively pulled hot exhaust gases across them, compounding the heat load, creating temperatures that exceeded the cooling capacity of the baffling system. Those cylinders were running lean, running hot, destroying exhaust valves, and nobody at Wright Field had noticed because their temperature sensor was in the wrong location. Landau sketched the airflow pattern on graph paper, drew the engine from the front, marked the propeller governor position, the distributors, the cowl inlet, the baffle arrangement, the counterclockwise swirl. he had observed during engine starts.
The hot cylinders matched the airflow pattern perfectly. The solution was obvious. Modify the oil delivery system. Route oil directly to the exhaust valve. Rocker arms. Cool the valves from inside. Bypass the inadequate external cooling. Use hollow mounting bolts.
Replace solid steel with drill-through versions that could carry oil to the exact components that were failing.
Simple drilling operation. Minimal machining.
No major structural changes required.
Wright would never approve it.
Their fuel injection program was already funded, already in development, already committed to production.
Admitting that
a squadron engineering officer on Guam had found a simpler solution would invalidate 2 years of engineering work, would embarrass senior leadership, would raise questions about why the problem had not been identified earlier.
Landau made the sketches anyway, calculated oil flow rates, identified which bolts needed modification, determined that 6 hollow bolts per engine would provide sufficient cooling to the critical valve stems.
He had everything ready, the complete engineering package, and on April 5, he requested a meeting with the wing engineering staff.
The meeting was denied. He was told to focus on operational readiness. On April 8, another B-29 burned during takeoff. 9
crew members died.
Landau watched from the flight line, watched cylinder 14 fail, watched the fire spread, watched the wing fold, and he knew exactly why. It happened. He had 6 days before his next scheduled meeting with the maintenance officer. 6 days to find someone who would listen before the next crew burned. The 20th Air Force was losing B-29s faster than Boeing could replace them.
Not to Japanese fighters, not to anti-aircraft fire, to engines that self-destructed during the most critical
phase of flight. Takeoff at maximum gross weight in tropical heat.
Northfield on Guam housed the 314th Bombardment Wing, 4 groups, 16
squadrons, over 120 Superfortresses. Elliefield on Saipan operated the 73rd Wing.
Northfield on Tinian operated the 313th Wing.
Together the 3 bases
launched missions carrying 10,000 tons of incendiaries monthly.
Burning Japanese cities, destroying war production, breaking enemy resistance.
Every mission started with the same calculated risk.
Engines at red line, before wheels left the ground. Pilots knowing that any cylinder failure in the first 60 seconds meant death for the
crew. No altitude for bailout, no time to recover, just impact and fire.
The statistics were classified,
but every squadron engineering officer knew them. 21 Bomber Command had lost 47 B-29s
engine fires since November 1944. Japanese fighters had destroyed 31 in the same period. American engines were killing more air crews than the enemy. Landau was not the only engineer who had noticed the cylinder failure pattern. A maintenance officer on Tinian had documented similar observations,
reported them through channels, received the same response.
Focus on operational readiness, let Wright Aeronautical handle engine design. The system was not set up
for field modifications. Changes required approval from Wright Field in Ohio.
Testing at Mlen Air Depot in California.
Production authorization from Air Material Command.
The process took months, even for minor modifications.
Meanwhile, crews were dying in patterns that could be predicted.
Landau knew which cylinders
would fail, knew which aircraft were most at risk, knew that maximum weight missions to northern Japan put the most
thermal stress on the exact cylinders that lacked adequate cooling.
He could predict failures, but could not prevent
them.
The fuel injection program was Wright Field's priority solution,
converting carbureted engines to direct
injection, eliminating the poorly designed elbow entrance to the supercharger, improving fuel-air mixture
distribution, all valid improvements, all addressing secondary problems while ignoring the primary cause. The cylinders were not overheating because of mixture distribution. They were overheating because cooling air never reached them. Direct fuel injection would cost approximately $88,000 per engine.
30,000 engines required modification, $2.6 billion.
6 months minimum to retrofit the Pacific Fleet, and it would not solve the valve cooling problem because it did not Address air flow to the critical cylinders. Landau's hollow bolt modification would cost less than $20
per engine, could be machined in any equipped maintenance shop, installed during routine cylinder changes.
Operational within weeks, but it required admitting that the official solution was incomplete. Required acknowledging that a field officer had identified something Wright's engineering staff had missed. The April 8th crash had killed a crew from the 29th Bombardment Group, men Landau knew.
Flight engineer he had worked with during formation training in Colorado, radio operator who played cards in the
enlisted club,
bombardier who had flown 16 missions over Japan,
all dead because cylinder 14 overheated during climbouts. The crash investigation would follow the standard pattern. Blame worn components. Recommend more frequent inspections. File the report. Move on. Nobody would ask why cylinder 14 failed instead of cylinder 1.
Nobody would analyze the airflow patterns.
Nobody would question why the designated worst case indicator never actually indicated worst case conditions.
Landau had the data, had the solution, had everything except
authority to implement it.
And the clock was running.
Missions launching daily. Engines failing predictably, crews dying while the bureaucracy processed paperwork. On April 14, General Curtis Lamia's staff announced a maximum effort mission. Every operational B-29 from all 3 islands, 500 aircraft, target Tokyo, maximum bomb load, maximum fuel.
Maximum gross weight, maximum thermal stress on engines that were already failing at unacceptable rates.
Landau did the calculations. At least 3 engine fires during takeoff, possibly 5, almost certainly fatal for the crews involved. And he still had no approval to implement his fix, no authorization to modify a single bolt on a single engine. He had 9 days before the maximum effort mission. 9 days to find someone who would listen or watch more crews burn. Landau spent April 15 drafting a
formal technical report, 8 pages, detailed airflow analysis, cylinder failure statistics by position, temperature data from multiple aircraft, sketches showing the counterclockwise vortex pattern, calculations proving that hollow bolts could deliver sufficient oil flow to cool the exhaust, valve stems, complete parts list, installation procedures, cost estimates, everything a competent engineering review board would need to authorize immediate testing. He submitted the report through proper channels.
Squadron engineering to group maintenance to wing
engineering, wing engineering to 21st Bomber Command technical staff. Each level of bureaucracy added another delay, another review cycle, another requirement for additional documentation. The April 16 response requested clarification on 17 technical points, questioned the validity of the airflow observations, noted that cylinder number 1 temperature data contradicted his conclusions since that cylinder rarely overheated, asked why Wright Aeronautical's engineering staff had not identified this issue during 2 years of intensive development work, suggested that field observations might be influenced by local operating conditions rather than fundamental design flaws. Landau rewrote the report, addressed every question, explained that cylinder 1's low failure rate proved his point rather than contradicting it.
The
sensor was in the wrong location, measuring the wrong data, creating false confidence in cooling system
performance, while the actual hot cylinders lacked any instrumentation. He attached photographs, added more temperature records, included testimony from mechanics who had replaced the failed cylinders. The April 18 response acknowledged receipt of the revised report, stated that the matter would be forwarded to Wright Field for expert evaluation. Estimated timeline for response 6 to 8 weeks. Thanked him for his diligent attention to aircraft reliability. 6 to 8 weeks. The maximum effort mission was in 7 days. At current failure rates, 21 Bomber Command would lose another 15 B-29s to engine fires before Wright Field even opened his report. Landau considered unauthorized testing, taking one engine, drilling the bolts himself, installing the modification, running the engine through a complete thermal cycle, proving the concept worked. But unauthorized modifications violated every regulation in the technical manual, could result in court-martial, could ground the entire aircraft if discovered, could cost him his commission and any chance of implementing the fix officially. He could also do nothing. Follow orders, maintain operational readiness, let the
system handle the problem through established procedures, wait for right field's response, except that some crews would die while bureaucracy moved at bureaucratic speed.
That was the safe
choice, the career-preserving choice, the choice that let him sleep at night, knowing he had followed proper channels.
But Landau kept seeing the April 8 crash. Kept seeing the wing fold. Kept
seeing 9 men die because a cylinder overheated in exactly the position his data predicted.
Kept knowing that his hollow bolt modification could have prevented it. Could prevent the next one. Could save crews on the maximum effort mission if anyone would authorize implementation. On April 19, AB-29 from the 39th Bombardment Group aborted a mission to Kagoshima. Cylinder 10 running hot.
Temperature climbing past limits.
Pilot feathered the number 2 engine. Returned to base. Emergency landing. No
fire, no casualties, just another aborted mission.
Another combat sortie. Lost to engine problems.
Landau inspected the aircraft.
Confirmed cylinder 10 was positioned exactly where
his airflow analysis predicted overheating.
Confirmed the cylinder showed early signs of valve distress. Recommended immediate replacement before the valve failed catastrophically. The maintenance crew pulled the cylinder. That night, while they worked, Landau measured the mounting bolts.
Standard 7/8 in diameter, hardened steel, solid.
Construction, simple to drill.
He had access to the machine shop, had the technical drawings, had everything needed to create the hollow versions, could make 6 modified bolts in 4 hours, could test fit them during the
cylinder replacement, could prove the concept before the next mission. Unauthorized modification, court
martial offense, career-ending decision.
But the maximum effort mission was in 5 days. 5 days until 500 B-29S launched at maximum gross weight. The oil delivery system was working, cooling the exhaust valve stems from inside, bypassing the inadequate external cooling that had killed so many crews. 10 minutes still, stable.
The flight engineer reported cylinder 10 holding steady at 360 degrees. Previous ground runs on this same engine had shown cylinder 10 climbing to 410 degrees. At the 10-minute mark, a 50-degree re-reduction, exactly what Landau's calculations had predicted.
15 minutes.
The test continued. Other maintenance personnel were starting to notice a ground run this long at full power was
unusual. The crew chief approached, asked why the extended test. Landau explained he was validating cooling performance after the cylinder replacement. Wanted to ensure the new
cylinder was properly seated.
The crew chief accepted the explanation. Walked away. 20 minutes. Cylinder 10 362 degrees. Cylinder 7 380 degrees. Cylinder 1375 degrees.
All the historically problematic cylinders were running cooler than baseline.
The hollow bolt modification
was working exactly as designed.
At 25 minutes, Landau signaled the flight
engineer to reduce power.
The test was complete. He had his data. Had proof that simple oil cooling could prevent the valve failures that had destroyed dozens of B-29s. Had evidence that Wrightfield's expensive fuel injection program was solving the wrong problem. The maintenance forms showed that
extended ground run, showed the temperature data, showed that something had changed in the engine's thermal
performance. Someone would eventually ask questions, someone would inspect the engine, someone would discover they unauthorized modification. But Landau now had proof of concept, had results that could not be dismissed as theoretical speculation. He spent April 22 documenting the test results,
comparing the temperature data against previous runs, calculating the thermal improvement, preparing a supplemental report to his original submission. The evidence was indisputable. 6 hollow bolts delivering oil to the exhaust valve rocker arms had lowered critical cylinder temperatures by an average of 47 degrees.
Enough to prevent valve failures, enough to save lives.
On April 23, Landau submitted the supplemental report containing the test results, requested approval for expanded testing, and proposed installing the modification on 3 additional engines, running them through full mission profiles, gathering comprehensive thermal performance data, and demonstrating that the solution was operationally practical.
The response arrived on April 25.
The 21st Bomber Command engineering staff acknowledged the test results, noted the temperature reduction, and authorized a formal proof of concept evaluation. Landau was instructed to prepare a complete test protocol, select 3 aircraft for modification, coordinate with Wright Field technical representatives, and carry out the evaluation under controlled conditions with thorough documentation.
Landau began preparations immediately.
He selected 3 B-29s from the 19th Group, arranged machine shop time to fabricate the hollow bolts, and coordinated with maintenance to schedule the installations.
Everything was approved.
Everything was authorized. Everything was finally moving through official channels with institutional support. The proof test was set for August 10, full engine runs, thermal mapping, oil flow verification, complete data collection.
Results would be forwarded to Wright Field.
If successful, the modification could be authorized fleet-wide, potentially saving hundreds of engines and preventing countless engine fires.
On August 9, the second atomic bomb fell on Nagasaki. Japan's surrender loomed.
The war was ending, and Landau's test schedule became instantly irrelevant.
August 15, Japan capitulated.
World War II concluded. The proof test was cancelled.
The hollow-bolt modification was never officially evaluated. Wright Field's fuel injection program became the post-war standard solution for our 3350 cooling issues. Landau's field modification was documented but never implemented, a solution that arrived too late.
He had identified the problem, traced the cause, developed the fix, and proven the concept, but the war ended before bureaucracy could authorize its deployment, before his simple modification could save the lives it was designed to protect.
Landau spent the remainder of August processing the 19th Group's return to the United States.
By December, he was back in civilian life.
The hollow bolts were forgotten. The counterclockwise airflow pattern was never officially recognized, and Wright Aeronautical's engineering records never credited a squadron engineering officer on Guam with identifying the AR-3350's fundamental cooling flaw.
Yet Landau knew that if his solution had been discovered and implemented earlier, there would have been no need for the expensive fuel injection conversion, no massive engine turnover, no loss of operational effectiveness. Japan was already on the brink of surrender before the atomic bombs. His modification, implemented in early 1945, might have shortened the war by weeks, potentially rendering the atomic bombs unnecessary. 6 hollow bolts per engine, $20 in modified parts, and dozens of crews might have survived. The Wright AR-3350 continued production after World War II, powering the Lockheed Super Constellation, Douglas DC-7, military transports, and long-range maritime patrol aircraft. The very same engine that had claimed the lives of dozens of B-29 crews became one of the most successful commercial aviation power plants of the 1950s.
Wright Aeronautical eventually resolved the cooling difficulties. Fuel injection eliminated carburetor problems. Redesigned baffling improved airflow distribution. Longer cylinders increased fin surface area. Enhanced quality control reduced manufacturing defects.
By the early 1950s, the AR-3350 reached 3,500 hours between overhauls. Specific fuel consumption fell to 4 pounds per horsepower hour.
Thermal management became dependable. Yet none of these advancements addressed the underlying airflow pattern.
Landau had identified the counterclockwise vortex, the stagnant zones behind the propeller governor and distributors, the cylinders that never received adequate cooling air. Wright's engineers simply increased the system's cooling capacity to compensate for inefficient airflow, a brute force solution rather than an elegant fix. The fuel injection modification Landau had regarded as unnecessarily expensive eventually became standard. Every AR-3350 received it in time. Billions of dollars were spent on a complicated solution when a simple field modification might have sufficed. But straightforward fixes proposed by field officers rarely compete with entrenched engineering programs supported by corporate contracts and Pentagon budgets. Landau's technical reports remained archived at 21st Bomber Command Headquarters and were later transferred to Air Force Historical Records. They exist today as evidence of a problem identified and solved too late to matter. His hollow bolt modification was never officially tested under controlled conditions, never evaluated by Wright Field, and never considered for production. The engineering establishment had invested too heavily in the fuel injection program to acknowledge that a squadron officer with keen observation skills and graph paper had discovered something they had overlooked. Recognizing Landau's insight would have required admitting that 48,000 previous engineering changes addressed symptoms rather than causes, that 2 years of development had ignored a fundamental airflow issue, and that the worst-case temperature sensor had been installed in the wrong cylinder. Organizations rarely admit such mistakes, especially when the alternative is quietly implementing a costly solution that achieves the same result.
Fuel injection worked. That it solved the wrong problem first became irrelevant once it resolved enough issues to make the engines reliable.
Darrell Landau returned to civilian engineering and never spoke publicly about his B-29 work.
His account of discovering the cooling issue appeared decades later in a book about World War II bombers. Just a few paragraphs, a brief mention, a footnote in the larger narrative of strategic bombing and the atomic age.
Yet those paragraphs matter. They document that someone observed the problem, understood the cause, developed a solution, and the system failed to act in time to save the crews who perished in the weeks between Landau's discovery and Japan's surrender. They failed to recognize that field observations sometimes reveal truths that laboratory analysis misses. The B-29 crews who burned during takeoffs in April, May, June, and July 1945 did not die because the problem was unsolvable. They died because the solution arrived through the wrong channels, at the wrong time, because bureaucracy moves slowly, because field modifications challenge established programs,
because simple answers make complex organizations uneasy.
If this story moved you as it moved us, do us a favor and hit that like button. Every like tells YouTube to share this story with more viewers.
Subscribe and turn on notifications.
We are rescuing forgotten stories from dusty archives every single day. Tales of engineering officers who saved lives with observation, hollow bolts, and the courage to challenge the system. Real people, real heroism. Drop a comment now and tell us where you are watching from.
Are you in the United States, United Kingdom, Canada, or Australia?
Our community spans the globe.
You are not just a viewer, you are helping keep these memories alive. Tell us your location.
Tell us if someone in your family served.
Just let us know you're here. Thank you for watching, and thank you for making sure Darrell Landau does not fade into obscurity.
These men deserve to be remembered, and you are helping make that happen.